Okay, let's get started. Any questions so far? Any questions? So far, so good? Good. So, we decided on which correspondence we're going to use in the Kakutani's fixed point theorem. But to make sure that we don't work in vain, let's make sure that a fixed point of this correspondence is a Nash solution. Well, it's pretty easy, but let's still do it. S star is a fixed point of B if and only if. Well, that by definition of a fixed point, S is an element of B of S, which by definition of B means S is S star is an element of the Cartesian product of Bi S minus I star, which just by definition of the Cartesian product for any I, the ith component of this vector should be in the ith set here. So Si star is an element of Bi of S minus I star. But that's if and only if. S star is a Nash solution of the game gamma. Okay? So if we can show that B has a fixed point, then we know that that fixed point is actually a Nash solution. So now let's try to show that every condition is satisfied. So we have to make sure that here S, the set of strategy profiles, is non-empty, compact, and convex. Well, that trivially follows. I will not go into that. Cartesian product of non-empty set is non-empty. Cartesian products of closed set is closed. Cartesian product of bounded set is bounded. So Cartesian product of compact set is compact. Cartesian product of convex set is also convex. You can easily show this. For this, you need to know a little analysis, but it's not much of a big deal. So the set of strategy profiles, well, the Nash theorem, which I just erased, in the Nash theorem, we assume that the strategy set of each agent is non-empty, compact, and convex. Hence, the set of strategy profiles is non-empty, compact, and convex. So this condition holds. Now we have to show that our correspondence is non-empty valued, convex valued, and has a did I erase it? Yes. Has a closed graph. Okay. So let's go one by one. B is non-empty. Valued. Well, what does that mean? It means that for any S strategy profile S, B of S is not empty. Well, what does that mean? Well, B of S was the Cartesian product of the individual best responses. So what this means is that for any S in capital S, for any I in N, Bi of S minus I is non-empty value. So this is equivalent to this statement. So how do we know that this is the case? How do we know that this is the case? Sorry? Yes, but that's what we're trying to show. How do we know that these are non-empty? Yes, sir. The what? Which theorem? Oh, but that's what we're trying to prove. We're trying to prove the Nash existence theorem, so I cannot use it. Actually, when we're working with the graphs, the pictures, that's what we used, right? Yep. So, okay, how do I use that condition? So how does these conditions imply, which of those conditions implies this? So again, what did we assume? We assumed, so we're assuming, I didn't write that part, so we're doing a direct proof, not a proof by contradiction. We're stated by saying that let gamma be a game for which the strategy set of each player is non-empty, compact, and convex subset of a Euclidean space. The preference relation of each agent is such that it admits a continuous numerical representation, which is quasi-concave, and it's in the component corresponding to agent I. So we assume that those hold. Yes, sir. Exactly. Continuity of, so by the way, this time it's not if and only if, so we have to be careful. The implication works upwards. This is the case since for each I in N, Ui is continuous. Well, let me go. So it's for each I, for each S minus Si, Ui, which is Ui given S minus I, is continuous, and capital Si is compact. This function has a maximizer, which means that agent I has a best response. Okay? So continuity in Si and compactness of the strategy set of agent I implies that his best response correspondence is non-empty valued, which implies that the Cartesian product of the best response correspondence is non-empty valued. So far, so good? So this is taken care of. And how did we take care of? Using the compactness of the strategy set and continuity of Ui in Si. Okay? So one more down, 2 to go. Convex valued. Guess what we're going to use for convex valuedness? Which condition will have a byte for convex valuedness? Again, what do we mean by convex valuedness? So actually, let me write that. By the way, when you're writing your implications, be careful. This is no longer if and only. Even if Ui is not continuous, Si not compact, we can have best responses. So this time we want to show that for any S strategy profile S, B of S is a convex set. So what does that mean? That's the case if and only if for any T prime, and I'll write the short version in B of S for any alpha between 0 and 1, alpha T plus 1 minus alpha T prime is also in B of S. So, which condition do you think will guarantee this? Exactly, right? That's what we had. When we had two best responses, we wanted to avoid the gap between them. And how did we avoid it? Using quasi-concavity of the numerical representation, right? So, again, we'll go. That's the case if and only if for every agent I, for any T prime in B of S for any alpha in 0, 1. This implies that alpha T, I should have written that for every I and N here. I'm sorry about that. It doesn't matter, they're all, well, that's what I'm going to get into, but they're all universal quantifiers, so we can change the order. Alpha Ti plus 1 minus alpha Ti prime is a best response of agent I to S minus I. Okay, that's what we want to show. But what does this imply? Okay, T in B of S implies, so let me move the for all I here. For all Ti prime in Bi of S minus I, that's what it implies, for any alpha in 0 and 1. Okay. So this is what we want to show, because this is equivalent to this. They're all if and only if. This is what we want to show. Okay? So, how do we show that? So, let I be in N, Ti prime B in Bi S minus I. Okay? So what does this imply? What does that imply? Actually, this is two-way for any Si in capital Si, Ui of Ti S minus I is greater or equal to Ui of Si S minus I. And the same thing is true for Ti prime. Okay. And these two have to be equal, because put Ti prime here, put Ti here, they have to be equal. So what is the next thing I would do? Yes, sir. Same upper counter set. Well, yes, so you have the idea, but let's formalize it a little bit in a little different way. The way we defined quasi-concavity, actually I said there's several ways to do it. I should have given the other way too, but we choose a level, right? So we choose, in the definition we had, we choose an L and show that about that level, the points at which the function takes a value about that level is a convex set. So what would you choose as L? Exactly, right? Choose one of these. So these two are equal, so let this be equal to L. So since Ui S minus I is quasi-concave, the set of all Si in capital Si for which Ui of Si S minus I greater or equal to L, which is Ui of Ti L, which is equal to Ui of Ti S minus I. Let me put a prime here. Is convex. Okay? So this set is convex. And what else do we know? Well, Ti is an element of this set. And Ti prime is an element of this set, which means that for any alpha between 0 and 1, alpha Ti plus 1 minus Ti, 1 alpha Ti plus 1 minus alpha times Ti prime is also an element of this set. So let me give a name to this set. Let's call this A for lack of a better symbol. So since A is convex and Ti prime are elements of A, we have, or any alpha between 0 and 1, alpha Ti plus 1 minus alpha Ti prime, an element of A, which implies Ui of alpha Ti plus 1 minus alpha Ti prime S minus I greater or equal to Ui of Ti S minus I, but that was greater than Ui of Si S minus I for any Si. I for any Si in calculus I. Which means that alpha Ti plus 1 minus alpha Ti prime is the best response. So that's what we wanted to show, and that's where we arrived. And the key here is, again, as your friend suggested, quasi-concavity of Ui in its own component. Okay? So far, so good? Any questions? So quasi-concavity of Ui guarantees that the correspondence is convex valued. So the next thing we have to show is the graph of B is closed, is a closed set. Okay? That's what we have to show. So how do you show that? So this time, okay. So want to show, what do we want to show? Graph of B is closed, is a closed set. Okay. So how do you show that? So rather than game theory, we're doing analysis now. How do you show that a set is closed? There are many ways, but the boundary must be included. So if you want to work with boundaries, then how do? You take neighborhoods of that. And so what other way can we do? What is one of the most effective ways of showing a set is closed? Complement is open, which again will probably work with boundaries. So, sorry? Convergence? So you take a convergent sequence. Okay. Exactly. So a set is closed. Okay. If you take a convergent sequence in the space that the set is contained, such that every element of the sequence is in your set, then the limit should also be in the set. So let me write that down. So this would mean that for any sequence, okay, SK, TK in graph of B that converges in S cross S. Okay. Take any sequence which is convergent in the space where this set lies. Okay. Then the graph, this set is closed if and only if the limit of this sequence is also an element of this set. Okay. If for any sequence that converges in S, we have limit sk tk as k goes to infinity, an element. So let's denote that with st is an element of the graph of B. Okay. Again, let me remind you what graph of B is. It's the set of, actually let me put a star here. It's the set of all st in S Cartesian product S such that T is an element of B of S. Guess which condition would guarantee this? Guess which condition would guarantee this? Sorry? I'm sorry, I can't hear. I have to. Compactness? Well, that might not be enough. Continuity of UI. Continuity of UI in all components actually would guarantee this condition. Okay. Should I write the proof of this part? Or are you saying enough? Sorry? It would be beneficial. So let's do it. So I take a sequence. Sequence in graph of B that converges to S star T star. Okay. So again, what do we want to show? My master's supervisor was Semih Koray Hoca. I took several courses from him, and one good habit that he had, one thing that I learned from him is when he was doing proofs, he would stop and write, want to show. It's always a good idea to write down in intermediate steps also, to write down where you want to go, because sometimes on the way we lose sight of where we want to go, okay? So I learned many things from him, and one of this, it might look like a small thing, but you know, when you're doing proofs, it makes a lot of difference. So we want to show that S star T star is in the graph of B, which is the same as saying T star is an element of B of S star. So this is what we want to show, okay? So when you're doing proofs, sometimes you should stop and write down what do you want to show, where do you want to arrive, okay? Okay, so what do we have? SKTK is in the graph of B. Any k natural number, SKTK in the graph of B implies, well, it's an if and only if, for any natural number n, tk is in B of sk, which implies for any k in n, for any I, for any agent I. Now we're going to have double subscripts. So let me write it like this: T I sub k is an element of B minus Bi S minus I sub k. Okay, which is the case for any natural number n for any agent I. So what does that mean? It means Ui, well, Ui S Ik S minus Ik is greater or equal to Ui Si S minus I. I'm sorry, I have a Tik, right? And for what? For every Si in capital Si. Okay, so far so good. So I just wrote what it means for Tik to be a best response of agent I to S minus Ik. Nothing fancy. Okay, so far so good. What is the next thing you would do? What is the next thing you would do? Sorry? Take the limit, but for us to take the limit, this k should be all the way here. But I can do that because these are all universal quantifiers. So we can interchange the order of universal quantifiers. So this is the case if and only if for every I in n, for every Si in capital Si, for every natural number n, okay, Ui of Tik S minus Ik greater or equal to Ui of Si S minus I k. Okay, now I have this statement. Okay, so let me refuel. So the next step is, as your friend said, take the limit, right? Well, we know that Ui is continuous in Si, the ith component. Okay, so as k goes to infinity, this approaches to T star. We know that Ui is continuous in S minus I. So as k goes to infinity, this converges to S minus I. This converges to S minus I star. Okay? And actually that finishes the proof. So the key is just interchanging the universal quantifiers and making use of the fact that Ui is continuous in all components. Okay? So that's which implies that Ti is a best response to S minus I. Ti star is a best response to S minus I star. Okay? Yes, sir. Ui is? Yes. So the continuity, we have the following theorem. I'll write the simple form. Limit as x goes to x bar, f of x is equal to f of limit of x as x goes to x bar. If f is continuous, we can interchange the function and the limiting operation. So that's where the continuity comes into play. Okay, so far so good. So all the conditions of Kakutani's fixed point theorem is satisfied. So Kakutani tells us that the correspondence B has a fixed point, and we know that that fixed point is actually a Nash solution of the game gamma. And that's it. Nothing fancy. I guess we can finish it by saying quite easily done. Okay? Any questions? Any questions? None? Okay, so that finishes the proof. Let's do one more example where we find Nash solutions of a game. The game that I'm going to talk about, is this thing working? I guess it is. It's going to take some time to warm up. So the game that we're going to consider is contributing to a public good. Because of my handwriting, I didn't want too much. I didn't want to write the story, so I have a short PDF file which gives us the story. So the game is contributing to a public good. Provision of a public good game. That's also how it's named in the literature. So we have two individuals who has to decide on how much to contribute to the provision, to the production of a public good. Okay? So as we read the story, let's do our modeling. So we have two agents. That means that N we can take as 1 and 2. The wealth of individual I we will denote by W, W of wealth, WI. We assume that WI is bigger than 0. Well, if it's equal to 0, again, the player, that individual doesn't have any role in the game. He cannot contribute anything. Each individual has to choose on how much to contribute for the provision, for the production of the public good. And any amount that is not contributed is spent on private goods. Okay? So essentially, this individual only has to decide on one thing, right? On how much he's going to contribute for the public good, or on how much he's going to spend on private goods. So one decision resolves everything. Yes, sir? So taxing? Well, at this moment, there's nothing about taxing. So let's finish the whole story. But the thing is, so it's me and you, and there's some public good. We each have to decide on how much to contribute. So if I decide to contribute, if I have 10 liras and decide to contribute 6 liras on the public good, I have 4 liras to spend on. Let's say that there's a single private good on that single private good. So essentially, for each agent, the strategy set of agent I is 0 to WI, right? If that's my total wealth, I can't decide, I can't contribute more than that. Contributing a negative amount is not meaningful, okay? So again, let's make a habit of it, where CI in capital SI denotes the action, of contributing CI liras, dollars, whatever, CI units to the public, to the provision of the public good. Okay? And the rest is spent as on private good. Okay? So far, so good? So that's the strategy set, and that's what a strategy, a number in the set, would mean. So the last thing about preferences. So each agent cares about the amount of the public good provided. Okay? So I contribute 2, you contribute 5, and then a certain amount of the public good is produced, is available for consumption, and we also consume our private good. We assume that individuals' preferences are such that they admit a numerical representation which is quasi-linear on money spent on private goods. By quasi-linear in money spent on private goods, we mean is the economists who took 203, you probably saw quasi-linear preferences, I assume, 203 or 204. Anyway, what it means is that the numerical representation of the agent can be written as, here we said it's quasi-linear, quasi-linear in money spent on the private good. So it means that the preference relation, the numerical representation of the preference relation of agent 1 is such that it can be written as the money spent on private good plus a function of the public good. Well, the amount of the public good depends on how much agent 1 and agent 2 contributed. So here, so this is a function of the public good, okay? And his utility can be written as B1 plus, so this should be 1, U1 of C1, C2 is equal, well, this should be this should be I. UI of C1, C2 is VI plus C1 plus C2. Let's say that this is the amount of the public good provided, plus money spent on private good. Okay? So that's what quasi-linearity means. Means that it can be written as the sum of the money spent on private good and a function of the other good, which is the public good. Okay? Well, what we assume about this function VI is that it's continuous. Well, we usually need continuity so that we can solve the maximization problem. Increasing, well, the more public good, the happier the agent is. Okay? As long as his private consumption doesn't change. Okay? Moreover, we assume strict concavity, which essentially means diminishing marginal, I don't like the word, marginal utility. Okay? So all seems to be reasonable, nice economic assumptions. So there's nothing crazy here, right? So far, so good? So, question, how much would each agent contribute to this public good? Okay, what would they play? What would they contribute? Or what should they contribute? Okay. So again, what we can do is, look for dominant strategies, strictly dominant strategies, which will be empty in this case. And then we will have to look for Nash. Okay. So, one question, what can we say about the existence of Nash solutions? Without solving this problem, can we say that this game has a Nash solution? How do we know? Well, let's look at the strategy set. It's a compact and convex set. Let's look at the numerical representation. Vi is continuous, and this part is also continuous, right? That's a linear function. So continuous plus continuous gives us a continuous function. So UI is continuous. What else? Well, fix C2, Vi is strictly concave. So it's strictly concave in C1 for any given C2. Well, every strictly concave function is, well, I'll get to that later. This part, this is a linear function, so it is concave and convex. A strictly concave function plus a concave function will give us a strictly concave function. Okay? So this function is strictly concave, which means that it is also quasi-concave. Every concave function is also strictly, every concave function is also quasi-concave. So UI is quasi-concave. But then all the assumptions of the Nash existence theorem is satisfied, which means that this game does have a Nash solution, at least one. Okay? So this game does have a Nash solution. The question is, what is it? Okay? Just before, well, we don't have that much time, but before we start attacking this problem, let's take a look. First of all, so that's the numeric representation of the preferences. We know from microeconomic theory 1 that any monotonic transformation of a numeric representation is also, any increasing transformation of a numeric representation is also a numeric representation, okay? So actually, I can just drop Wi from here, okay? And nothing will change. It will represent, it will still represent the same preference relation. So rather than taking that, we can just take this. We don't have to carry this extra baggage. Okay? We don't have to carry this extra baggage. It makes life a little bit, so I'll just spend less ink. Okay? This preference relation, this function, and this function represent the same preference relation. So drop the Wi, we have something simpler. Moreover, you know, I can assume Vi of 0 to be equal to 0. If it's some number a, you know, subtract a from here, you'll get the same numeric representation. And then, you know, take Vi C1 plus C2 minus a as your function v. That function will still be continuous, increasing, and strictly concave. So without loss of generality, we can take Vi of 0 equal to 0. It doesn't make much of a difference. Okay? So, given all these, now we can try to solve this. But we have one problem. We don't know what the function Vi is. But my claim is, even though we don't know what the function Vi is, we can still say something about the Nash solutions of this game. And that's why I like to work with this game. So it will be, we will solve it in a general functional form. No matter what Vi is, as long as it satisfies these conditions, we'll be able to solve that problem. Okay? Any questions? Any questions? Okay. So, before we attack, it would be a good idea to think, so let's take UI to be this function, which is, you know, drop the extra baggage here. What can we say about this function UI? What can we say about this function UI? We know that it is continuous, being the sum of two continuous functions. We know that it's strictly concave, being the sum of a strictly concave function and a concave function. Right? So those are things that we know. Okay? Sorry? Yeah. So it always has. So because the domain is compact, okay, because the domain is compact and the function is continuous, there's always a best response. So what would that look like? Well, I would like to make use of this fact, the way that this function is defined. one observation that you can make easily is ui of C1 plus C2, 0, is equal to what? Oh, let's take 1. Is equal to minus C1 minus C2, right? But what is this animal? Right? Right? Or U1 of C1, C2 is equal to U1 of C1 plus C2, 0 plus C2. So what? What good does that do us? Sorry? U1 is increasing in? Increasing in what? Which component? In C2. How do you know that? When, oh, from here, if C2 increases, this number increases. We know that this function is, so U1 is increasing in C2, yes, okay. So what? What good does this do? Let's go back to pictures. Pictures are very powerful tools. Okay. So let me draw the graph of so we know that given any C2 here, okay, what do we have? We have a strictly concave function of C1. So I don't know what the exact shape is, but let me just draw something maybe like this, okay? It might be going down, it might go up like that. So let's say that this is U1 of 0. Okay. Actually, let me make it even simpler. So let's go down. So we have a maximizer here. Okay. My question is, what does U1 of C1, C2 look like? What does U1 of C1, C2 look like? It's the same translated. C2 units above. So because of C2, you're saying that it shifts up by C2 units. Okay, is that all? And to the left, which is actually the important part, right? So because of this, what you get is, let me use a different color. So you shift this to the left by C2 units. So I'm going to be bad at drawing this, okay? And then you shift it up by C2 units. So, okay? So far, so good? So far, so good? Well, unfortunately, we have to stop here. Time is up. Okay, I forgot to give that 10. Did I give that 10 this sheet? Yes, I did. Okay, so think about it. Look at this picture. what does this imply about the best response of player 1? You see, because of that quasi-linearity, if I know the picture for C2 equals to 0, I can essentially know the picture for any C2. Okay? That's it. Think about it. We'll talk about that